Welcome back to the Math Behind ChatGPT. This is episode 3, Coding Self-Attention in Python. In the last episodes, we explored the big picture and the core math behind self-attention. Today, we will bring that math to life in code step by step. Here is our roadmap. First, we will build queries, keys, and values. Then we will walk through the self-attention pipeline, dot product, scaling, softmax, and weighted sum. Finally, we will package this into a function, explore multi-head attention, and link it to PyTorch. Let's recall the formula. Attention equals softmax of Q times K transpose divided by the square root of D all multiplied by V. Each step serves a purpose: similarity, stability, normalization, and context aggregation. Our code will mirror this flow exactly. We will start in Python with NumPy. To keep things simple, we will import NumPy as np and set up a short sequence of 4 tokens. Each token will have an embedding size of 8. This small setup helps us to see the shapes clearly and understand how the process works. Once the idea is clear at this scale, it becomes much easier to extend the same approach to larger real-world examples. Now that we have our token embeddings, the next step is to project them into 3 different spaces, such as Q, K, and V. Q stands for queries. They represent what each token is trying to find. K stands for keys. They describe what each token has to offer. And V stands for values. They hold the actual information that will be passed along. Think of it like a conversation. Queries are the questions being asked, keys are the labels on the answers, and values are the content of the answers themselves. In practice, this is done by multiplying the embeddings with 3 separate weight matrices: one for Q, one for K, and one for V. These weight matrices are learned during training. For our demonstration, we will generate random embeddings and random weight matrices just to see the shapes and mechanics in action. From there, we compute Q, K, and V by simple matrix multiplication. The next step is to measure how strongly each token relates to the others. We do this by taking the dot product of Q with the transpose of K. The result is then a similarity matrix. Each row corresponds to a single token, and the values across that row show how much that token is related to every other token in the sentence, including itself. In simple terms, this matrix tells us which tokens should pay attention to which others. After computing the similarity scores, we apply a scaling step. Each score is divided by the square root of dk, which is the dimensionality of the key vectors. This scaling is important because it keeps the values in a reasonable range. Without it, the numbers could grow too large or too small, which would make the softmax function unstable. By normalizing in this way, the model can focus more effectively on meaningful relationships between tokens. Then, next transform the scaled scores into probabilities. We do this with the softmax function, which we apply row by row. To keep the calculation stable, we first subtract the maximum value in each row before exponentiating. This prevents numerical overflow. The result is then a probability distribution for every token. Each row now tells us how much attention that token should give to every other token in the sequence. Finally, we combine the attention weights with the values. We do this by multiplying the softmax weights by V. The result is a new set of token representations. These are context-rich embeddings that blend information from across the entire sequence. In other words, each token is no longer isolated. It now carries knowledge about the other tokens it decided to focus on. Now that we have seen each step individually, we can put everything together into one clean function. The process starts by projecting the input embeddings into Q, K, and V. We then compute the dot products between queries and keys to measure similarity, scale the scores to keep them stable, and apply the softmax function to turn them into attention weights. Finally, we multiply those weights by V to produce context-aware representations. This compact function captures the entire self-attention mechanism in just a few lines of Python code. In practice, self-attention is not limited to a single head. Instead, multiple attention heads run into parallel, each with its own set of parameters. This allows different heads to specialize in different aspects of the sequence. For example, one head might capture grammatical structure, another might focus on long-range dependencies, and another might emphasize semantic meaning. The outputs from all these heads are then concatenated and projected back into the model's embedding space. Think of it as having several specialists working together, each bringing a unique perspective and then combining their insights into one unified representation. Here is the PyTorch equivalent of the self-attention mechanism. PyTorch provides nn.MultiheadAttention, which implements the same underlying math we just explored so far. The difference is that it is optimized for efficiency, handling batches, and applying masks automatically. In language models, we often use a casual masks. This ensures that each token only attends to previous tokens and itself, never to future tokens. This is essential for generating sequences in a step-by-step autoregressive manner. Today, we turned the self-attention formula into Python code. From QKV projections to multi-head attention, you now know every step. In episode 4, we will assemble the full transformer block with residuals, normalization, and feed-forward layers. Thanks for watching. Stay tuned.